In this video, we're going to talk about the magic limit shortcut, otherwise known as L'Hopital's rule. So by the end of this lesson, you should be able to answer the following little question. How can knowing about derivatives make some of those algebra limit solving strategies we learned about easier? And just as a reminder, by the end of Unit 2, so we're almost done, Lesson 12 will be the last lesson in Unit 2. You should be able to answer the following big questions, or at least begin to answer them. How do we make finding derivatives easier, and what is the point of finding derivatives? So for the first part of this unit, we've been really looking at how do we make finding derivatives easier. We've talked about power rule, product rule, quotient rule, and what that does, those rules allow us to find derivatives a bit more easily than using the limit definition. Now, in these last two lessons, what we're going to look at more is what is the point of finding derivatives. So, like, what do derivatives allow us to do rather than just finding the derivative? Like, why is finding the derivative important? So, let's look back at your notes from lessons 3 and 4, and I'm not going to pull them up here, but you should pause the video and look at those really quick. What issues did we encounter in solving limits algebraically that motivated our different limit solving strategies? So one I can think of right off the bat is when direct substitution gave 0 over 0. That was a bad situation. We couldn't do that algebraically because we couldn't divide by 0. And so what that does, or what that did, was that inspired us to use things like factoring or rationalizing the numerator. Or something like squeeze theorem. So we had all of these algebraic strategies for when we would come up with an issue with using direct substitution to solve a limit. So what we're going to do now is sort of talk about this case of 0 over 0 and some other cases just like it, and how can we deal with those in a little bit more systematic way. So an indeterminate form is a limit that may or may not exist. So we don't know which it is. There are two main types. We have type 0 over 0 or type infinity over infinity. And so to show what we mean by indeterminate, consider these two examples. So if we were to go ahead and solve this first limit with the algebra strategies that we know, so in this one we probably want to factor and simplify, we would get that the answer to this limit is 2, whereas if we looked at the limit of x over x squared as x approaches 0, we'd find that it does not exist. So let's think about in both of these cases what would happen if we tried direct substitution. So here, if we tried direct substitution, we get 1 squared minus 1, which is 0, over 1 minus 1, which is 0. And the same in the case over here. We'd have 0 over 0 squared, which is 0 over 0. So both limits are of type 0 over 0, but one evaluates to a finite number, that's this one, while the other does not exist, and that's that one. Okay, so that's the idea of an indeterminate form. When we do direct substitution, do we get some kind of expression involving zeros or infinities, which we can't be certain exactly what the answer is just based on what that direct substitution gives us. So some other indeterminate forms that we'll encounter in this lesson are, we could have products, so we could have 0 times infinity, we could have infinity minus infinity, we could have 1 raised to the infinitieth power, we could have 0 raised to the 0 power, or we could have infinity to the 0. So those are our only other types of indeterminate forms. Something like, I'll write this in red so it's clear that this is not correct, but something like 0 to the infinity is not indeterminate. Okay, so it's not just any combination of infinities and ones and zeros, it's very specific combinations. So if it's not the things listed here, then it's not indeterminate. Okay, so as I was kind of saying earlier, we were able to solve some limits involving indeterminate forms using algebraic strategies. So like with our factoring, rationalizing the numerator, squeeze theorem, we were able to take care of a lot of those 0 over 0 cases, but now what we want to do is actually learn about a more systematic method for dealing with such limits, and we can do this now because we know how to actually compute derivatives in a very efficient way. Okay, so now we come to the main point of today's lesson. So to solve limits involving indeterminate forms of type 0 over 0 and infinity over infinity, we use L'Hopital's rule. So this is a French name, so get used to pronouncing your French names there. It's not Le Hospital, it's L'Hopital. So I've even given you like a pronunciation guide there. Okay, so suppose f and g are differentiable functions, and that makes sense because if we want to use derivatives, well, we better have some functions where the derivatives exist. And we just want to say that the derivative of g is not 0 on an open interval I. All that's taking into account is that we're dealing with quotients. Now, here's the main part. If the limit, as x approaches a, of f of x over g of x is of type 0 over 0 or infinity over infinity, then the limit of the ratio of the two functions is equal to the limit of the ratio of their derivatives, or the quotient of their derivatives. Okay, so ratio and quotient, same thing. So this very mathematical statement here has been translated into sort of a plain English statement right here. Okay, so this is like our mathy version, and this is our I guess, plain English version. Okay? So what we mean by the notation is basically we can take the derivative of the top function, we can take the derivative of the bottom function, and the resulting limit will have the same answer as the limit that we started with. Okay? Now, very important to note, so I'm going to highlight this, bold it, like I don't know how else to say it. This is not the quotient rule. Okay, so we're dealing with quotients or ratios, but this is not the quotient rule. Okay, it's actually a lot simpler than the quotient rule, but it's not a shortcut for the quotient rule either. Okay, this is completely different. So the quotient rule is a method for evaluating derivatives. Okay, L'Hopital's rule is a method for evaluating limits. All right, so they are not the same, and I see that all the time with students. They get the two things confused because they're both quotients, but quotient rule goes with derivatives, L'Hopital's rule goes with limits, okay? So hopefully that sticks. All right, so let's dive into some examples. So the first example we're going to do is the limit as x approaches infinity of ln of x over the square root of x. So first, we must check that L'Hopital's rule can be used. So remember up top, we can only use L'Hopital's rule if we have type 0 over 0 or infinity over infinity. So the first step is always to do some kind of direct substitution and determine if we can get one of those two types. So if we think about ln of infinity, so it's not really good practice to plug in infinity, but that's kind of what we're thinking about here. We want to think about what happens to natural log as x gets very, very large. Well, what happens is we don't have any horizontal asymptotes or anything, so ln of x grows without bounds, so we get infinity. And square root of x, the same thing happens. So the bigger x gets, the bigger square root of x gets, and it never settles on any kind of number. So the top function and the bottom function both go to infinity, so therefore the limit is indeterminate of type infinity over infinity, and we can use L'Hopital's rule because it falls into one of our two classes. Okay, so now that we've determined we can use the rule, let's actually evaluate the limit. So in this first example, all the steps are written out for you, but we're going to go through and say why they're true. Okay, so we start with our problem statement, as always. So we recopy the problem. And the first thing we can do is apply L'Hopital's rule. So anytime you're applying L'Hopital's rule, make sure over the equal sign to write a little h so that you're indicating that you're taking the derivative. And that's just a really nice thing to do for your grader. So I'm going to put a little arrow here that says indicates use of L'Hopital's rule. Okay, so just put a little h over the equal sign. All right, and so that'll also help you when you're looking back at your own work. You'll realize exactly where you took the derivative. So what we're going to do from step 1 to step 2 is take the derivative of the top. So maybe I should use a highlighter here too, just so it's a little more obvious. So if we take the derivative of ln of x, we end up with 1 over x. And if we take the derivative of square root of x, we get 1/2 x to the minus 1/2. So that's just a simple power rule. Okay, so we say in step 2, we apply L'Hopital, which means take derivative of top and bottom. All right, now from step 2 to step 3, what we want to begin to do is just simplify this, this function that we're taking the limit of as much as possible. So the first step I'm going to do towards that is rewrite all of my exponents using negative exponents. So I'm just trying to get everything in terms of like everything has an exponent, so I could just do some easy little arithmetic on there. So I rewrite 1 over x as x to the minus 1, and here we're just dividing 1 over 1/2, so I went ahead and flipped the 2 to the top. All right, what we can do from there is do some algebra or arithmetic on the x with the exponents. So we think about -1 minus a -1/2 would give us minus 1/2. And so we're still simplifying here, but that's kind of what is going on. Maybe I should write this over here. So we have -1 minus -1/2. So we're simplifying our exponents. And then I can rewrite this as a radical in the denominator. So we didn't have you do this with derivatives, but now it's kind of important to be able to rewrite those powers of x. If you have a negative power, rewrite it in the denominator. If you have a fractional power, rewrite it as a root. So that way, it's obvious whether or not you can use L'Hopital's rule again. So here we get 2 over the square root of x, which is pretty obvious that we're not going to be able to use L'Hopital's rule again because, well, the numerator's 2, so we can't get a 0 over 0 or an infinity over infinity. And so we just use direct substitution, and we know that if we have, actually, no, let's not call this direct substitution. Let's call this a true fact. Okay, and the true fact we're using here is the limit as x approaches infinity of 1 over x to the n is equal to 0. So remember, square root of x is just a power. So x to any power in the denominator with a constant on top is going to approach 0 as x approaches infinity. So we get that our overall answer is 0. Okay, let's look at another example. So if you want, you can pause the video, try this yourself, but I'm going to keep explaining it as well. So next we want to figure out, can L'Hopital's rule be used to evaluate the limit as x approaches pi from the left of sine of x over 1 minus cosine of x? So to check if L'Hopital's rule can be used, we try direct substitution and check for 0 over 0 or infinity over infinity. So that's exactly what we're going to do here. So if we do sine of pi over 1 minus cosine of pi, the sine of pi is 0 and the cosine of pi is -1. So we get 0 over 2. Well, 0 over 2 is not 0 over 0, nor is it, well, I'll write like this. Okay, and 0 over 2 is not infinity over infinity. Thus, we cannot use L'Hopital's rule here. And actually, we wouldn't want to anyway, because when we substituted this in, we got 0 over 2, which is just 0. So that's the answer to our limit, and we don't actually need an extra rule to deal with that. So it is tempting to use L'Hopital's rule everywhere now that you know derivatives. So it's easy to look at a limit problem and just say, well, if I just started taking derivatives of this top and bottom, it'd be really easy to get the limit. But it's important, so important. So it's so important that I'm going to highlight this again. It is important to remember that L'Hopital's rule has very specific conditions that must be met before it can be used. So once again, we can only use it in the case of quotients that substitute to 0 over 0 or infinity over infinity. Okay, so that's the very first step. Every single time you must check for that. So let's try a couple more examples that are a little more difficult. So our next example, we're going to evaluate the limit as x approaches 0 from the right of x times ln of x. So we don't have a quotient anymore, so this is going to be a different indeterminate form than we've done so far. So first, we analyze the problem to see what exactly type of indeterminate form that we have. So as x approaches 0 from the right, the first factor, x, approaches 0. Plug in 0 for x, well, it's just 0. The second factor, ln of x, approaches negative infinity. And again, that comes from the graph of ln, so if we think about what's happening to ln close to 0, we see that it decreases without bound. So that's going to be negative infinity. So this limit is indeterminate of type 0 times infinity, because first factor is 0, second factor is negative infinity. So that's one of our other indeterminate types. Now, we cannot use L'Hopital's rule unless we can manipulate the product to become an indeterminate quotient. So remember, L'Hopital's rule, we must have 0 over 0 or infinity over infinity. Right now we have a product, so we need to manipulate the problem in order to use the rule. Okay, so we start with our problem statement. And we do a little bit of finagling here to get a quotient. So what I'm going to do is I'm going to take this x and I'm going to rewrite it as a quotient of 1 over x. Okay, now this might seem like it makes the problem more complicated, but in fact it's algebraically equivalent to the first problem statement, but we've rewritten it as a quotient. So what we've done here is we've moved x to the denominator as x to the minus 1. So just like when we move stuff from the bottom to the top and we change the exponent to negative, same thing if you move it from top to bottom, but x to the minus 1 is just equal to 1 over x. Okay? Now, if we test this limit for indeterminacy at this point, ln of 0 is infinity, and 1 over 0 is also infinity. Okay, so we have type infinity over infinity. So we can apply L'Hopital's rule. Okay, so for L'Hopital's rule, remember we write the equal sign with the little h, and we take the derivative of the top function and the bottom function. So we have the limit as x goes to 0 from the right. ln of x, the derivative of ln of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. Okay, and then we want to simplify this as much as possible. So we have the limit as x goes to 0 from the right of x to the minus 1 over negative x to the minus 2. And I'm going to simplify this one more step to be the limit as x approaches 0 from the right of negative x to the 1. Negative 1 plus 2 is 1. Yeah, okay, so we have the limit as x goes to 0 of negative x, which is just 0. So evaluating the limit, we just plug in 0 for x, and we get 0. Okay, so that's how we work through the problem with L'Hopital's rule. Now, one question I want to ask, so at this point you should pause the video and kind of think about this a bit. From the first to the second step, why didn't we do this instead? So why didn't we take ln of x instead of x and move it to the bottom? Okay, so same trick that we did, just choosing the different function. Well, let's see what happens if we do this. So if we test for L'Hopital's rule, so let's do 0 over 1 over infinity, which is 0 over 0. Okay, so we can use L'Hopital's rule. So can use L'Hopital still. But let's see what happens. So if we use L'Hopital, we get the limit as x approaches 0 from the right of 1 over ln to the minus 1. So let's rewrite ln of x to the minus 1. So this is going to require a chain rule. So we get negative 1 times ln of x to the minus 2. So let's rewrite this as a fraction. So we have the limit as x approaches 0 from the right of 1 over negative 1. Actually, let's do it this way. We can just move that ln of x to the negative 2 to the top. So we have negative ln of x squared. Okay, now let's think about the problem here. Well, the problem here is that, actually, no, I don't want to do that because that's going to get rid of my quotient. Okay, so here I could recheck if we can use L'Hopital's rule. Okay, and we can't because our numerator is 1, but also what we've done is we've made the denominator more complicated. So here, denominator is, oh wait, my bad, I made a mistake, so I didn't finish out the chain rule. Okay, let me restart this from the beginning. All right, so we're doing chain rule. So we have negative 1 ln of x to the minus 2. Then we need to multiply by the derivative of ln of x. Silly me. So we have 1 over x here. Okay, so we do need to simplify this a little bit. So we get the limit as x approaches 0 from the right of x over negative ln of x to the minus 2. Okay, so at this stage, I still have a quotient. Great. I still have an indeterminate form, though. So what this did is this kind of just made my function more complicated. So this made the limit more complicated. Because like now, I have a more complicated chain rule in the denominator. I still have x in the numerator, so like it didn't really get me anywhere from where I started. So the goal of L'Hopital is to make the limit simpler. Okay, and what do I mean by that? Well, I kind of mean things like reduce the power on whatever function you're dealing with, okay? So we want to reduce powers. We want to eliminate extra terms, etc. So there's a few more things you could think about, but I don't want to give you like a laundry list of a bunch of rules to memorize. The idea is just when you apply L'Hopital, the thing you get after taking the derivative should look nicer than what you started with. So maybe you have to do a little bit of simplifying, but overall it should look simpler. So if it doesn't, try picking a different function to manipulate. Okay? So let's look at another example, and this is going to be a different indeterminate form than we've done already. So let's compute the limit as x goes to 1 from the right of 1 over ln of x minus 1 over x minus 1. So let's check for our indeterminate form. So we have 1 over ln of x as x approaches 1 is going to go to, let's think about this. So 1 over ln of 1. ln of 1 is 0, 1 over 0 is infinity. Okay, and 1 over x minus 1, we have 1 minus 1 is 0, 1 over 0 is also infinity. So the limit is indeterminate of type infinity minus infinity. Okay, so to use L'Hopital's rule, we must manipulate the difference into an indeterminate quotient of 0 over 0 or infinity over infinity. So we start with our problem statement. And a good rule of thumb here, we've got two fractions that are being subtracted. Why not just subtract them? To me, that's the most natural thing to do. So we find an LCD, so least common denominator, and that's going to be x minus 1 times ln of x and subtract the fractions. So if we do that, we should get this second step of x minus 1 minus ln of x over x minus 1 times ln of x. And at this point, we have a quotient, so let's check for an indeterminate form. So if we plug in 1, we get 1 minus ln of 1 all over 1 minus 1 times ln of 1. So this is equal to 0 minus 0, ln of 1 is 0, over 0 times 0. So again, ln of 1 is equal to 0. So this is indeterminate of form 0 over 0, meaning we can apply L'Hopital's rule. So we write our little equal sign with the h to signal that we're applying L'Hopital's rule, and we take the derivative of the top and the bottom. So first, if we take the derivative of x minus 1 minus ln of x, we get 1 minus 0, derivative of 1 is 0, minus 1 over x. So the derivative of ln of x is 1 over x. And now for the denominator, so actually let me highlight this to show that that's our derivative. Now let's take the derivative of the denominator. So we have a product of x minus 1 and ln of x, so we need to apply product rule. So we have x minus 1 times 1 over x plus 1, so derivative of x minus 1 is 1, times ln of x. And so let's just highlight to color coordinate for you there. So we have our denominator here, we have our derivative of the denominator there. Okay, so let's do a little bit of simplifying. So this is just going to be some routine algebra. So we have the limit as x approaches 1 from the right. I'm going to combine the two things on top, so I have x minus 1 over x all over. If I distribute the 1 over x, I have 1 minus 1 over x plus ln of x. I can take another step and combine that denominator. So I have the limit as x goes to 1 from the right of x minus 1 over x all over x minus 1 plus x ln of x all over x, and I can take one more step and just rewrite this as a product with the reciprocal. So limit as x goes to 1 from the right of x minus 1 over x times x over x minus 1 plus x ln of x. Okay, so that's a bit complicated of some algebra, but hopefully it doesn't look too unfamiliar. It just might take a little bit of practice to get used to doing certain calculations like this again. So finally, if we cancel the two x's there, we end up with the limit as x approaches 1 from the right of x minus 1 over x minus 1 plus x ln of x. Okay, so all of that was now so we can check for an indeterminate form again. So far we've only used L'Hopital's rule once in each problem, but you could use it more than once. So we want to check for our indeterminate form again. So we plug in 1 again, so we have 1 minus 1 over 1 minus 1 plus 1 times ln of 1. And simplifying gives us 0 over 0 plus 1 times 0, which is still unfortunately 0 over 0. So we must apply L'Hopital's rule again. So taking the derivative of the top, so let me color code this again for you. So we're going to have our numerator and we're going to have our denominator. Okay, so the derivative of the numerator is just 1. Derivative of x minus 1 is 1. Derivative of x minus 1 plus x ln of x. So from the x we get a 1, the negative 1 is a 0. Now we need a product rule for the x ln of x. Okay, so get ready. So we have x times 1 over x plus 1 times ln of x. Okay, and well, that's it for that derivative. So let's think about how we can start to simplify this again. So what I can do first is multiply the x times 1 over x, and that gives me the 1 in the denominator. So I have 1 plus ln of x all under 1. And then I can combine the 1 plus 1. So I can add 1 plus 1, and I get 1 over 2 plus ln of x. And then now I can finally use direct substitution. Okay, so if I plug in 1 for x, I get 1 over 2 plus 0, which is 1/2. So we'll say direct sub and simplify. Okay, so this example in particular should show you that not every L'Hopital's problem is super nice. Okay, this one is quite messy. We had algebra to start off with. We had to combine fractions. Then we had two applications of L'Hopital's rule, each one that required checking if we could actually use L'Hopital's rule. And then finally, after those two applications, could we actually use direct substitution? So when you think of L'Hopital's rule, it shouldn't always make you think of it being like this wonderful shortcut that you can do just all of the problems from the first unit with. Okay, sometimes it is quite messy. But also, I don't think we could have done this problem in Unit 1, so it did help us a little bit, even though it's not super, super nice. Okay, so that was the indeterminate difference. Now what we're going to look at is an indeterminate power. So this is probably the hardest type of L'Hopital's rule problem that you might see. So finally, we're going to calculate the limit as x approaches 0 from the right of 1 plus sine of 4x, all raised to the cotangent of x. So now at this point, you're probably like, okay, now she's just getting ridiculous with these functions. But it turns out that these are things that we could not possibly have done in the first unit. So now L'Hopital's rule is very, very useful for doing things like this. But it's going to require some very specific algebraic finagling to handle it. Okay, so let's check for our indeterminate form to begin with. So as x approaches 0 from the right, 1 plus sine of 4x gives us 1 plus sine of 0, which is just, well, 1? Yeah, that's a 1. Sine of 0 is 0, so we have 1 plus 0, and that gives us 1. Cotangent of x. Now this one's kind of tricky. Cotangent of x, if you remember your graph of cotangent, and we're approaching 0 from the right, it sort of looks like this. So it's almost like a backwards tangent that's been shifted a little bit. So as we approach 0 from the right, cotangent of x is going to infinity. Okay, so the limit is indeterminate of type 1 to the infinity, and this is an indeterminate power. So we could use L'Hopital's rule as long as we can manipulate it to become a 0 over 0 or infinity over infinity. Now here's where it's going to get a little bit rough. So what we're going to do is we're going to sort of take the limit in a roundabout way. So our goal is to get this big exponential expression to give us a limit, but it's kind of hard to deal with as it sits right there. So what we're going to do is find a way to get that exponent out of the exponent. And the way to do that is with logarithms. Okay? So if you haven't seen logarithms in a while, now would be a good time to go back and refresh your memory on that. So what we're going to do is we're going to just define a variable for the entire expression in the limit. Okay, so we're going to let y, let me change this to yellow. We're going to let the letter y equal to the entire thing inside of the limit, and we're going to manipulate it a little bit with logs. So the first thing we're going to do is take the log of both sides. So take the natural log of both sides. And what this allows us to do is bring cotangent of x to the front. So that's a rule of logarithms where if you have something like, how do I write this? So like if I had ln of x squared, that's the same thing as 2 times the natural log of x. Okay, so that's kind of what we're doing in this step right here. So maybe I'll put that in a thought bubble, so you know that it's actually not part of the problem, but it's kind of like a simpler example of what we're doing there. Okay, and now what we can do is use the fact that cotangent of x is equal to 1 over the tangent of x, and we can rewrite our expression with a tangent in a denominator. Okay, So that's a bit confusing. So if that's confusing, make sure you pause the video here and let that part of the problem marinate before moving on to the L'Hopital's part, which is the next part. Okay, but for those of you that want to move on right away, check for indeterminate form as x approaches 0 from the right. So what we're going to do is we're going to take this entire expression here and we're going to plug in 0 and see what happens. So we have the ln of 1 plus sine of 4 times 0 over tangent of 0. Okay, so let's see what this evaluates to. So we have ln of 1 plus 0, which is 1, over tangent of 0, which is 0. So sure enough, this is 0 over 0, and we can use L'Hopital's rule. So we indicate that we're using L'Hopital's rule, and then we take the derivative of the top of the function and the derivative of the bottom. So let's see what colors I should pick here. Let's do blue and pink. So numerator, I'm going to color code blue, and denominator, I'm going to color code pink, just so you see where those derivatives are corresponding down here. And so if I take the derivative of the top, I have ln with something sitting inside of it, so I'm going to need a chain rule. So I'm going to get 1 over 1 plus sine of 4x times the derivative of 1 plus sine of 4x. So derivative of 1 is 0. Derivative of sine of 4x is 4 cosine of 4x. So that's another hidden chain rule in there. And the derivative of tangent x is just secant squared of x. Okay, so this gets a little complicated. So next what I can do is I can combine the numerator to, so we're combining the numerator here, and use the fact that secant squared of x is equal to, actually let's write it like this so it's less confusing. 1 over secant squared of x is equal to cosine squared of x. So that's why I was able to write a cosine in the numerator there. So maybe let's color code this again just so you see where all the parts are coming from. So this was the original blue part, as was this. This right here was the pink part in the previous step. So at this point, we're working on simplifying our expression to either use L'Hopital's rule again or solve with direct substitution. Either way, I'm going to have to plug in 0 in this next step to, see if it's, warranted that we use L'Hopital's rule again. And so what I get from that is 4 times the cosine of 0, or 4 times 0, which is 1, times cosine of 0 squared, which is 1 squared, over 1 plus sine of 4 times 0. Sine of 0 is 0. So our final answer is 4. Now, stop there, pause the video if you're getting confused again. If not, let's plow along. So now we've found that the limit as x approaches 0 of ln of y is equal to 4. Okay, so this is really important. So we found a limit, but it's not the limit that we need. Okay, we've finished the roundabout part of the limit. But remember, at the very beginning of this problem, we made this initial substitution of y is equal to this big thing in the limit. So we found the limit of the natural log of y, but we need